Prepare to rethink everything you thought you knew. This is Mind Benders, your source for the most mind-twisting facts that will expand your understanding of the world. Let's bend some minds.
The Hook. September 1st, 1859. In telegraph offices across North America, the mundane click-clack of communication is violently interrupted. Sparks leap from the machines, shocking operators and setting telegrams ablaze. In Boston, a telegraphist disconnects his machine from the battery, only to find it continues to transmit messages, powered by a strange ethereal current from the sky itself. The network, humanity's first great technological web, is convulsing. But the strangeness isn't confined to technology. That night, the sky erupts, not just in the far north, but everywhere. Brilliant auroras of red, green, and purple light up the night sky so brightly that newspapers can be read as if it were dawn. Gold miners in the Rocky Mountains wake up and start making breakfast, thinking the sun has risen early. In Cuba, ship captains log sightings of crimson lights dancing directly overhead. People in the Caribbean, who have never even heard of the Northern Lights, gaze upwards in wonder and fear. They didn't know it, but they were all witnesses to the single most powerful geomagnetic storm in recorded history, an event so immense it dwarfed anything seen before or since. A solar superstorm. They called it the Carrington Event. In 1859, it was a beautiful and terrifying curiosity. If it happened today, it wouldn't just be a light show. It would be the end of our world as we know it. Part 2. The core premise. To understand the threat that lies dormant 93 million miles away, we have to go back to that morning, hours before the chaos began. We have to meet the man who gave the event its name, Richard Carrington, a wealthy English amateur astronomer. Carrington wasn't just a hobbyist, he was meticulous. His passion was observing and sketching sunspots, those dark blemishes on the sun's surface. On September 1st, as he projected the sun's image onto a screen, he witnessed something no one had ever recorded before. A sudden, intensely brilliant flash of white light erupted from a large group of sunspots. He described it as a white light flare. It was blindingly bright, even on the projected image, and lasted for 5 minutes. Carrington had just become the first person to directly observe a solar flare. He suspected a connection between the flare and the magnetic disturbances felt on Earth a day later, but he couldn't prove it. Today, we know exactly what he saw. He witnessed the trigger for a colossal coronal mass ejection, or CME, aimed directly at our planet. Imagine the sun not as a steady, peaceful ball of light, but as a boiling, dynamic cauldron of plasma and magnetic fields. Sometimes these magnetic field lines, which are often tangled and complex, suddenly snap and realign. This releases an incredible amount of energy in the form of a solar flare, a burst of radiation. But often this flare is accompanied by something far more significant, the ejection of billions of tons of solar plasma and magnetic field into space. This is a coronal mass ejection. Most CMEs miss Earth, harmlessly blasting into the void. But the one Carrington saw was different. It was aimed directly at us. And it was fast, exceptionally fast. While a typical CME takes 3 to 4 days to reach Earth, this one made the 93 million mile journey in just 17.6 hours. It was a cosmic cannonball, and Earth was directly in its path. Part 3. The Deep Dive. The impact of this plasma cloud on Earth's magnetosphere, our planet's protective magnetic shield, was biblical. The shield was compressed so violently that it induced massive electrical currents, not just in space, but on the surface of the planet itself. These are called geomagnetically induced currents, or GICs. In 1859, the only piece of large-scale electrical infrastructure we had was the global telegraph network, and it became the canary in the coal mine. The GICs surged through the long telegraph wires, which acted like giant antennas. The voltage was so high it overwhelmed the primitive systems. Reports flooded in from across the world. The American Telegraph Company's office in Boston reported that their machines were throwing sparks powerful enough to burn through paper. In Pittsburgh, an operator reported that a stream of fire was coming from the circuits. In Norway, telegraph lines were reportedly set alight. This wasn't just a disruption. The Earth's own magnetic field was generating usable and dangerous electricity. The famous story from the Boston office, where operators disconnected their batteries and sent messages to Portland, Maine for 2 hours straight, only the auroral current was proof of the storm's incredible power. Narrator: the scale of the solar eruption itself was immense. Modern analysis estimates that the energy released was equivalent to 10 billion atomic bombs. The cloud of plasma that hit Earth was vast, a turbulent magnetic behemoth. For over a century, the Carrington Event was a historical footnote, a story told by astronomers. But then, scientists found a way to look back in time. By drilling deep into the ice sheets of Greenland and Antarctica, they can analyze ice cores that contain a layered record of Earth's atmosphere stretching back thousands of years. When a massive solar storm hits Earth, it creates certain nitrates and other isotopes in the atmosphere that then fall and get trapped in the ice. Scientists analyzing these layers found a massive spike in nitrates corresponding to the year 1859. The spike was more than twice as large as any other solar storm in the last 500 years. The Carrington Event wasn't just a story, it was a physical scar left on our planet. Part 4. Answering Key Questions. This discovery in the ice raises the most important question of all. Could a Carrington-level event happen again? The answer, unequivocally, is yes. It's not a matter of if, but when. Solar flares and CMEs are a regular feature of our sun's activity. They happen all the time. What makes an event catastrophic is a combination of 3 factors: strength, speed, and direction. We need a powerful, fast CME aimed directly at Earth. So, what are the odds? Based on historical data from ice cores and modern observations, scientists believe a Carrington-level storm is likely to occur, on average, every 100 to 150 years. Given that the last one was in 1859, you can do the math. We are living in the window. In fact, we've had some close calls. In July 2012, a CME of Carrington-level magnitude erupted from the sun. It was a monster, but it missed. It passed through Earth's orbit about a week after we had moved past that point. Had it occurred just a few days earlier, you might not be watching this video right now. How much warning would we get? Thankfully, unlike an earthquake, a solar storm isn't instantaneous. We can see them coming. Satellites like NASA's Solar Dynamics Observatory and the Solar and Heliospheric Observatory are constantly monitoring the sun. When a CME erupts, we see it. The warning time depends on the speed of the CME. For a Carrington-class event, we might only have 17 or 18 hours of warning. For a more typical storm, it could be 2 to 3 days. This gives us a precious but short window to prepare. To power down satellites, disconnect sensitive parts of the power grid, and brace for impact. Part 5. The Unseen Consequences. So, let's run the thought experiment. A Carrington-level event is detected. It's hurtling towards us. The 18-hour countdown begins. What happens when it hits? This is where the story turns from history to a terrifying modern reality. Our civilization is built on a skeleton of electricity and digital information. The GICs from a Carrington event wouldn't just surge through telegraph wires, they would surge through our high-voltage power grids. The primary point of failure would be the extra high-voltage transformers. These are the backbone of any national grid. These transformers, some the size of a small house, would heat up, melt, and explode. They are not easily replaced. They are custom-built, weigh hundreds of tons, and have a manufacturing lead time of months, sometimes years. A 2013 report from Lloyd's of London estimated that a Carrington-level storm could knock out enough transformers to plunge 20 to 40 million people in the U.S. alone into darkness for a period of months, potentially lasting over a year. But the blackout is just the beginning of a domino effect of catastrophic failures. Think about your life. Without electricity, there's no light, no refrigeration, no heating or air conditioning. Municipal water pumps would fail, cutting off clean drinking water and sanitation within days. No power means no fuel pumps. The entire transportation network would grind to a halt. No trucks to resupply grocery stores, no trains, no fuel for emergency vehicles. Supermarket shelves would be bare within 72 hours. But the most profound impact might be on the invisible systems we rely on. The internet would be gone, your phone a useless brick. But it's worse than that. Global finance is entirely digital. Stock markets would cease to exist. Bank accounts, credit cards, ATMs, all inoperable. The global economy would effectively be. Then there's GPS. The storm would damage or destroy most of our orbiting satellites. Without the precise timing signals from GPS, everything from aviation and shipping to precision agriculture and even cell phone tower synchronization would fail. The intricate dance of global logistics would collapse. This isn't an inconvenience, this is a regression, a cascading systemic failure that would push our interconnected, just-in-time society back to a pre-industrial age, but without the skills or local infrastructure to survive it. The death toll from starvation, disease, and social breakdown would be unimaginable. It would be a civilization-ending event. The story of the Carrington Event is a tale of two eras. In 1859, it was a moment of cosmic wonder. Today, its ghost haunts our fragile technological world. The sun, the source of all life and energy on Earth, is also the source of our greatest existential threat, a threat that is not hypothetical, but inevitable. So, are we doomed? Are we just waiting for the sky to fall? Not necessarily. The greatest difference between us and the people of 1859 isn't our technology. We know this threat exists, and we can prepare. Governments and power companies are slowly beginning the process of hardening the grid, developing new types of transformers and installing circuit breakers that can better withstand these geomagnetic currents. It's an expensive and slow process, but it's happening. Our ability to forecast space weather is also improving dramatically. Missions like the Parker Solar Probe are flying closer to the sun than ever before, helping us understand the physics that drive CMEs. Future missions are being designed specifically to act as an early warning system, giving us more time to prepare for an Earth-directed storm. The Carrington Event is a reminder of our place in the cosmos. We live on a tiny, fragile rock, subject to the whims of a powerful star. Our global civilization, for all its wonders, is a delicate construction. But humanity has always faced existential challenges. Our story is one of overcoming them through foresight, ingenuity, and collaboration. The threat of a solar superstorm is not a reason for despair, but a call to action, a call to build a more resilient world, to invest in the science that protects us, and to remember that for all our power, we are still part of a vast and untamed universe. The sun will throw another tantrum. The only question is, will we be ready when it does?
The world is full of fascinating paradoxes, isn't it? We hope today's facts truly bent your mind. If you're ready for more daily revelations that challenge the norm, subscribe to Mindbenders. Don't forget to ring the bell so you never miss a new video. Until next time, keep questioning.